Hi, I'm Frederick. I will present ARB, an efficient implementation of arbitrary-precision midpoint-radius interval arithmetic. And what is this about? In some fields, like number theory and computer algebra, we sometimes need to compute with very high precision, perhaps hundreds or even thousands of digits. We also want to be absolutely sure that we get correct results. There are a few approaches. The most common is floating-point arithmetic. The widely used MPFR library guarantees correct rounding for atomic operations. But we need to do error analysis for more complicated calculations, and this can be very hard. Interval arithmetic solves this problem by enclosing every quantity by a lower bound and an upper bound, tracking the error automatically. The MPFI library uses two MPFR numbers for the endpoints. The drawback is that this doubles the cost. The third option is ball arithmetic. An interval is now represented by high precision midpoint and a low precision radius. This is more efficient for precise intervals. Ball arithmetic has been used before, but there was no low-level library with a wide range of optimized functions. So what is ARB? ARB is an open-source C library for ball arithmetic. The library runs on all common platforms, is thread-safe, and extensively tested and documented. Some of the main features are: first, an efficient implementation of numbers in midpoint-radius format. The internal representation contains a number of technical improvements, such as dynamic allocation of the midpoint, a dedicated type for error bounds, and support for arbitrarily large exponents. This design is explained in detail in the article. Second, ARB provides comprehensive support for complex numbers, polynomials, power series, matrices, and special functions. Third, ARB uses asymptotically fast algorithms for large input. Finally, ARB's built-in functions limit their computation time according to the requested precision, which saves the user from having to detect certain problematic input in advance. This slide shows timings for basic real arithmetic at precision between 64 bits and 32,000 bits. We see that at high precision, ARB generally runs about as fast as MPFR and twice as fast as MPFI, which uses endpoint-based intervals. Some more complex operations, such as powering, shown in the bottom right, are even faster in ARB than in MPFR. Polynomial multiplication is an important kernel operation for many tasks. On this slide, we see the time to multiply polynomials with real and complex coefficients for degree between 10 and 100,000 and precision between 100 and 10,000 bits. ARB is significantly faster than MPFR-CX, which uses a floating-point FFT without providing any guarantees about the error. In fact, ARB not only tracks error bounds automatically, it uses an exact algorithm internally, which gives much better error bounds than a numerical FFT. One application is to compute number theoretical functions, such as the partition function, which counts the number of ways n can be written as a sum of positive numbers. The best way to compute P of n uses a rather complicated infinite series of transcendental terms. If this series is approximated correctly, we can round to the nearest integer and hopefully get the right result. But it's very easy to mess this up. For example, older versions of the Maple computer algebra system sometimes gave the wrong result for the partition function. Using ball arithmetic, we can compute an interval which is guaranteed to contain the answer, and when this interval contains exactly one integer, then we certainly have the right value. Now, an important point is that ARB scales to very high precision. For example, ARB takes 0.3 seconds to compute the number of partitions of 10 to the 10, which has 100,000 digits. This is a bit faster than an implementation of the same algorithm using MPFR for high precision terms and hardware doubles for low precision terms. It is 200 times faster than Mathematica. ARB was used to compute the number of partitions of 10 to the 20, which has 11 billion digits. This took 200 CPU hours, about half of which were spent computing just a few terms to extremely high precision, and half was spent computing more than a billion terms to low precision. Finally, ARB implements a large number of different mathematical special functions, including gamma function, Bessel functions, hypergeometric, and elliptic functions. All functions have full support for complex parameters, and many functions also support computing derivatives. Even if you don't need interval arithmetic, a nice use of ARB is to compute mathematical functions of ordinary floating-point numbers. By iteratively increasing the precision, we can guarantee that the output is accurate to any given tolerance, for example to full 53-bit double precision or 113-bit quad precision. We can even guarantee correct rounding with this method. Comparing ARB's output with MPFR actually revealed examples where MPFR computed incorrect results. I hope you found this interesting. For more details, please refer to the paper in Transactions on Computers or the ARB documentation website.